Hey everyone, you might know me from our socials, but I don't think we've ever been formally introduced. I'm Sharyar. I'm a dev advocate here at Educative, and you're going to be seeing a lot more of me today because we're going to be talking about one of the most foundational concepts in computer science, which is two pointers, and also later we're going to discuss a variation of that called fast and slow pointers. This kind of pattern pops up a lot in MAANG interview questions and just interview questions in general, especially during screenings. And so it's important for people to know how to deal with this kind of question, even if it appears in like a weird way. Because a lot of times these interview questions will try to trip you up. But yeah, we're going to talk about the pattern today, and hopefully you'll be able to recognize it when it shows up for you. So let's just get into it. Let's start by understanding what exactly two pointers are and how we can apply them and why we need them in the first place. So let's say we've got an array of 6 numbers, n is equals to 6, n is the length of the array. 0, 1, 2, 3, 4, 5. And let's say we want to find, actually let's make it n is equals to 7. Let's add one more. All right, we've got an array with numbers from 0 to 6. And let's say we want to find numbers within the array, pairs of numbers within the array that sum up to a particular number. We'll call it k. So in this case, let's say that k is equals to 4. A typical approach to this would just be to run a nested loop and then find numbers that would sum up to the number that we're looking for. So that would be something like for I in range n, for j in range n, if the array at I plus the array at j is equals to k, we save the sum to some kind of collection, a list or a set or whatever you choose to save it in. Now, this kind of approach will work, but we have a nested loop here, which is going to take O of n square time. And as the array gets longer, that's going to become prohibitive. So what can we do to kind of reduce that time complexity and make it work faster? We can use two pointers. So let's just copy that array over really quickly. And then we can see how two pointers applies to this kind of question. All right, so the way that two pointers work is it's very self-explanatory. We have two pointers at each end. And what we're going to do is we're going to look for certain conditions that will help us decide how to move these pointers. So we know in this case that we're looking for numbers that sum up to k. And in this case, k is equals to 4. So let's just start by seeing if 0. Actually, let's start by naming our pointers so we can refer to them later. Let's call this the left pointer and let's call this the right pointer. All right. So we're going to start by seeing if our left and right pointers are greater than, less than, or equal to our k, which is 4. So 0 plus 6 is greater than 4. What should we do? We know that this is a sorted array, and for two pointers, you always need a sorted array. We should move our right pointer to a lesser value because we're looking for a sum that is equal to our k. And we know that if we move our left pointer to the right, we're going to end up with a sum that's even greater than what we have now. So we're looking for something that approaches towards the sum that we're looking for. So we're going to move our right pointer one step to the left. Let me add that. Move right. Now we're going to repeat the same step. We're going to see if the sum is less than, equal to, or greater than our k, which is 4. And it's still, oops, that's supposed to be 5. It's still greater than 4. We're going to do the same thing. We're going to move our right pointer over, and then we're going to do our comparison again. So 0 plus 4 is equals to 4. That's what we're looking for. We're looking for a pair that sums up to 4. So we're going to save that somewhere. And we have two choices here. We can move our right pointer to the left, or we can move our left pointer to the right. It wouldn't make that big of a difference. You're just going to be switching a step back and forth. So I'm going to choose to just move our right pointer over to the left again. And now it's pointing at 3. So 0 plus 3 is less than 4. Now what are we going to do? This is a case that we haven't really seen before. We know that we're looking for a sum that equals to 4, and the sum that we have now is less than 4. So we want a sum that's greater. So we're going to do the exact opposite of what we did in the beginning, and we're going to move our left pointer to the right. So left moves here. And now we have 3 plus 1, which is equal to 4. And once again, we're going to save it, and we're going to move our right pointer over to 2. Oops. There we go. And then we're just going to keep going. So we have 2 plus 1, right? Yeah. We have 2 plus 1, which is less than 4. So we're going to move our left pointer. My screen is stuck in it. Okay, there we go. We're going to move our left pointer, and now our left and right pointers are pointing at the same index. That means we've explored the entire array, so we can stop looking. We found the same 2 pairs that we found with our nested loop, but we've done it with of n time complexity. And that's why 2 pointers is an important approach to have in your back pocket, because you can do things much faster than you can with like a different computational method. And, you can always do things that have a very high time complexity within certain constraints in interview questions. And so you need to know how to be able to adjust based on the constraints that are given to you when you're doing those questions. So the approach that we just looked at involves 2 pointers at the ends of an array moving inwards, but 2 pointers can also have 2 pointers in an array moving in the same direction. And we're going to look at that when we look at fast and slow pointers. But for now, let's just do a question really quickly and see how we can apply this kind of algorithm in practice. And we're going to do a very popular question called valid palindrome. All right, so I have our interview prep feature open here, and you can see that, it has this introduction to 2 pointers, which covers almost everything that I just talked about. And this is a really helpful feature for someone who is just getting into these patterns and looking to kind of have something that can help them understand these problems in a way that is natural and easy to understand. And you can see you have all of these diagrams. Those really help me. And, it's text-based, so you can easily understand everything. You can use AI to summarize them. You can understand with examples. You can see when this pattern, is a good fit for the problem that you're doing. You can take practice quizzes, and you can solve problems. So let's just start solving problems. We've got valid palindrome here. It's an easy question. This is one that's very popular with Meta especially. So given a string S, we're going to return true if it is a palindrome. Otherwise, we're going to return false. Pretty straightforward. A phrase is a palindrome if it reads the same backwards and forwards. And we're going to turn it into a lowercase string before we do anything. And we're going to remove any non-alphanumeric characters. Yeah. And these are our constraints. You can see that the length of the string is going to get really long, and that's why a nested loop would not work in this case. So we're going to go with the 2 pointers approach. So let's just start by declaring our 2 pointers here. I'm going to call them, actually, let's just call them left and right so that they're synonymous with what we just discussed. All right, we've got our 2 pointers at the opposite ends of our string. You can just think of the string as an array of characters, if that makes it easier, which actually, that is exactly what a string is, so that is how you should think about it. But if you're new to this, then yeah, think of the string as an array of characters. All right, while left is less than right, because remember, our breaking condition was when left and right are pointing to the same thing. We have certain conditions here that we're going to need to take into account, which is that only alphanumeric characters should be considered. But let's just deal with that later. And let's add a comment so we remember to do that. And we're also going to have to lowercase our string. Let's just do that inside the loop. So if s at left dot lower, so we're going to turn it into a lowercase character, is not equal to s at right dot lower, we're gonna do something. So let's just come up with a palindrome that we can use here, something easier than this. What's a one-word palindrome? Let's Google something. These are too long. Civic. All right, so we've got our word. So our left pointer is currently here, and our right pointer is currently here. Let's comment this out. And what we're gonna do is we're gonna start comparing our values at our left and right pointers to see if they're the same, because in any palindrome, they're gonna have to be the same. And if they're not, then we know that the string is not a palindrome, so we're gonna return false. And if they are true, like if they are the same, we're gonna move our left and right pointers inwards, and we're gonna start comparing the next letters in the sequence. So we're gonna move our left pointer up by 1, and we're gonna move our right pointer down by 1. All right, let's run this. We should probably have some test cases passing, but not all of them. Yeah. All right, this is because we haven't really considered non-alphanumeric characters. So let's go over this example. We've got 1, 2, 3, 3, 2, 1. Actually, not this one, because we don't have, maybe something like this. We have special characters that are non-alphanumeric, and we're gonna have to skip all of them to get to what we actually have to compare. So what we're gonna do is just repeat our breaking condition, and s at left, right? So what this is doing is, let's say we have a string that looks like this. We're gonna ignore these because we're not considering non-alphanumeric characters. So we're gonna move our left pointer forward until we encounter a character that is not alphanumeric that is valid for us to consider. And then we're gonna do the same thing on the right, but we're gonna move it backwards. And we're gonna change this to right. And let's see, all of our test cases are passing. That is great news. Let's just submit this. And we're good. All of our test cases passed, and we've solved the is valid palindrome problem. All right. So now that we have a pretty good understanding of how 2 pointers work, let's move on to fast and slow pointers. All right, let's talk about fast and slow pointers. Fast and slow pointers are pretty much exactly what they sound like. They are variants of 2 pointers, but one pointer is moving faster than the other. So let's go over an example really quickly so you know what I'm talking about. Fast and slow pointers are typically used in linked data structures where there's some kind of element which is dictating how you're going to move. So you can have a linked list. There's some problems where you have an array where the element of the array is telling you how many steps to move forward, and things of that nature. So let's say we have a linked list like this, and we have our 2 pointers initially pointing at the same position, which is our head pointer or head node. And like I said, this is one of those cases where the pointers are moving in the same direction, but with different speeds. So we've got our fast pointer and we've got our slow pointer. So let's say our slow pointer in one iteration moves forward by 1 step. Our fast pointer might move forward by 2 steps. And we can use this to perform certain tasks. Like, this is really popularly used to find maybe the middle element of a linked list. Sometimes it's used to find the nth element of a linked list. It's really popular to find cycles in a linked list. There's an algorithm called Floyd's tortoise and hare algorithm or cycle detection algorithm, which we will be covering later. But for now, let's just see how fast and slow pointers can help us find the middle element of a linked list. So we've got, okay, I'm just going to call them S and F. You've got our fast and slow pointers, and slow in each iteration is going to move forward by 1. Fast in every iteration is going to move forward by 2. All right, so we're going to do our first iteration. Fast goes here, slow goes here. And then again, fast move forwards by 2 steps. So fast goes here, and slow moves forward by 1 step. So slow goes here. All right, now there's nowhere for fast to go because it's reached the end of our linked list. And you can see that slow is pointing towards the middle element of our linked list. And that is how fast and slow pointers can help us find, the middle of a linked list. But you can also have fast and slow pointers adjusted to different speeds so you can find the nth element of a list. So you would start moving the slow pointer maybe n iterations after you start moving the fast pointer. And that's pretty much how they work. Very similar to 2 pointers, but they have a different use case. Let's go over the code to solve a linked list cycle problem, and then we can see how to put this, what we've just learned, into practice. All right, so we're going to do a problem called linked list cycle. It's an easy problem, so let's just get into it. We've got the head of a linked list, and we're going to determine whether the list contains a cycle. And a cycle exists if a node in the list can be revisited by continuously following the next pointers, as we know. Pretty self-explanatory. Return true if a cycle is present, otherwise we're going to return false. All right. So this is what our node structure looks like in this linked list. We've got a value, and we've got our next pointer. So let's start by initializing our slow and fast pointers at our head pointer. So they're both initially pointing towards the same position. And then we're going to do while something. So I'm just going to write true for now. We're going to move slow forward by 1. So that's going to be slow.next. And we're going to move fast forward by 1. This might be a good chance for you to pause and think about what fast might be, but I'm just going to continue. It's going to be fast.next because we're going to move it forward by 2 positions. And what we know from Floyd's cycle detection algorithm is that if we have slow and fast pointers moving and there's a cycle, then eventually they're going to catch up with each other. And the fast pointer is going to lap the slow pointer. So if slow is equals to fast, we've got a cycle. And we're going to return true. Otherwise, if this doesn't happen, we've got return false at the end. So we can just deal with that on its own. And now let's just discuss this while true situation. That is not our condition, but let me explain what the actual condition for this will be. All right, so let's look at these 2 lists and let's see how they can help us determine what the conditions for a loop should be. So we've got a linked list that is of even length. We've got 4 nodes, and our fast pointer initially is pointing at the head of the linked list. And let's just see how it's going to move. So we're moving it forward by 2 steps. After the first iteration, fast is going to end up here. And at the second iteration, fast is going to end up here. So the last element of a linked list typically just points to none. So fast is going to end up being none. So fast does not exist. Now let's look at the case where we have an odd length linked list. Fast initially starts at the head pointer. We move it forward. Fast ends up here. Now fast exists, but fast.next does not exist. And that's going to cause problems. These 2 cases are going to cause problems when we try to move our fast pointer forward here, unless we deal with those in our loop or we have some kind of exception handling. So what we're going to do is in our loop condition, we're going to use the cases that we just discussed here, and we're going to make it while fast exists and fast.next exists to handle both the even length linked lists and the odd length linked lists. All right. And now if I run this, we should pass all of our test cases. But there is another case that we haven't really considered, which is if we have a linked list that's either empty or if we have a linked list that is only made up of one element, in which case we're going to have issues moving our pointers forward. So let's just deal with that edge case at the beginning. So we have if head is none or head.next is none. Head is none means our linked list does not exist, it's empty. And head.next is none means that we have a linked list which only has one element. And in both of those cases, you can't have a cycle. So we're going to return false. Now let's just submit. We should pass all of our test cases. And we did it. All right, so we've solved our problem. We've learned how two pointers work. We've learned how fast and slow pointers work. And you can head over now to educator.io/interview if you want to do more problems like this. We've got a bunch of different resources that you can use to help figure out how these patterns work. We've got a bunch of different problems which are organized by company, so you can organize your prep by company that you're targeting. And we've got a bunch of features within our offering that you can use to kind of get better. So for example, we've got code feedback here. Tells me that I've implemented this perfectly, which is good to know. But let's say I make a silly mistake, which I often do. And now you can see it says debug instead of getting code feedback. And it's telling me to carefully consider how I move the faster pointer. So it's kind of pointing me towards the right direction and telling me how I should be thinking instead of just giving away the solution right away, which is really helpful because when you're in an interview, you kind of want to have a sense of what you're supposed to do and not just get the right answer right away. So you can grow as, a programmer. Let me fix that really quickly. We've got our understand with examples button. So if you're a visual learner like me, you can go over these. You can, kind of run through the algorithm in your head, see what you can do. We've got our ask feature. You can clarify questions, clarify constraints, and just generally be ready for your interview when it comes. So thank you so much for joining me, and I will see you next time.